Hey guys, hello everyone. My name is Vinit. I am a routing escalation for Cisco TAC. I work with basically anywhere routing is involved on Cisco platforms. I get pulled into most of the escalations. We are going to talk about seamless MPLS. Hope there's seam and nothing less. So. The other name of seamless MPLS is also unified MPLS, so don't get confused if you see somewhere unified MPLS or seamless keyword interchanging in the slides. What we're going to talk about today is what are the current mobile market conditions, what is really happening, what are the requirements, scale requirements, convergence requirements, stuff like that. We'll get an overview of seamless MPLS, what it is, what are the technologies involved in it, how does the whole solution integrate into one single solution to scale the whole mobile transport network. We'll be looking at the components, and we'll go through some of the design case studies or use cases on how you can deploy seamless MPLS in the network. And once we are done with that, I am free for the rest of the day, so we can have some good amount of beers or any other alcohol that you want. All the alcohol is on Jason, so don't hide, Jason. All right. So what do we have in the current market conditions for the mobile transport? You have eNode Bs, the endpoints where you have like 100 megs of links or the radio networks being deployed. You have 1 Gbps access connecting the eNode Bs. Then you have the 10 Gbps on the aggregation layer, and on the core you have the 100 gig. You need higher convergence and or seamless integration of new services that the service providers want to deploy. Like you have MPLS L3 VPN services, the LT services, or Layer 2 VPN services, all the kind of services. At the same time, you do not want to make changes across your whole network, your MPLS network that you have deployed. So you need a high scale, but at the same time, you need to be supporting all sort of services from all different locations, right? Obviously, because of the scale, the amount of scale you have, and with the number of growing requirements for mobile transport or mobile data, the services needs to be optimized. Obviously, you cannot scale properly if the services are not optimized and not providing you with optimal services at different locations. Say for you are using a service on your mobile phone, you switch to an iPad, and then you switch to your home laptop or your office laptop. You do not want to see a difference in the kind of services that you use on any of the devices that you are having. You want a seamless and the most optimal service across all those different devices or boxes that you're using. Apart from that, it's also important that the topologies or the network that we have at different locations or at central location is supportive of modification. It supports mixed topologies, and it can support the upcoming future technologies. So say for when they migrated from 2G to 3G and now to LTE, and in future you have 5G coming up. So your network should be supportive enough that you can migrate easily from one technology, from one service to another service. And these services are nothing but the kind of applications that will be using the network infrastructure that you already have in place. So you want that an architecture across the board which could seamlessly migrate or allow you to upgrade the network infrastructure and provide you better services. Like I said before, you need a graceful insertion of or deployment of new services and integration into the existing infrastructure. Now, you already have MPLS domain. How many of you are familiar with MPLS or worked on MPLS? Quite a lot of people, right? So MPLS allows you to get rid of the routing-based lookups and do the label-based lookups and do the forwarding based on that, right? Makes it faster for switching the packets within the core. Now, when you have so huge scale of services deployed in your network on your access layer, what you need is faster convergence. So you want the end users or end customers not to experience the delay for any kind of voice or video data. Now remember, based on the market survey, it has been assumed that by 2018, this year, 70% of the mobile data is going to be video, right? For other kind of data, 400 to 500 milliseconds of delay is okay. Your routing convergence can take up to 400 to 500 milliseconds or up to a few seconds. But with other technologies, you reduce those convergence times. But if you have video data, you cannot tolerate a higher rate of convergence time, right? You need that convergence to be quicker enough, to faster enough, from 50 to 100 milliseconds, and this way so that the end user do not experience any kind of flickering in the video feeds or any kind of data loss when they are using high bandwidth data. So you need the faster convergence. Now it's tricky enough if you have a huge network on the service provider side, and if you're using traffic engineering or traffic engineering with fast reroute, the deployment can be pretty complex based on how you're deploying your T tunnels. And the challenge comes in primarily when you're trying to break your network into different segments and your IGP routes. Now, what happens is, say you have like 50 routes around your access layer. If you combine multiple access layers and share the routes at the aggregation layer, you will have somewhere around 2,500 routes. From 2,500 routes to your edge network will be somewhere around 10,000 or plus routes. And at the core, somewhere around 60 to 70,000 routes. Now, having those amount of routes in your IGP table is not a scalable way. Obviously, you will face convergence issues, right? Database exchanges, all those things will happen. So you do not want those. And at the same time, we also want to break down our routing domain, your IGP domain, into subsections so that it makes it easier for troubleshooting purposes. I am from TAC, and I have always followed the rule, a simple rule of elimination. Eliminate which is not relevant, right? So the question I asked, how many of you have worked on MPLS? I did the process of elimination. It was good for me because rest people will have fewer questions for me. Okay, so I do that often. And we all need to do the process of, follow the process of elimination from time to time. So for provisioning and troubleshooting purposes, you all obviously need to break down your routing domain. Now, in this, with your regular MPLS, it's hard to do that. But if you try to do that and you want to run scalable services, you want to have any amount of services deployed at any time, at any given location, without making too many changes across your network, we need unified MPLS or seamless MPLS. Now, what is seamless MPLS? Seamless MPLS gives you an efficient MPLS transport architecture. It gives you a hierarchical model of which is not available with regular MPLS LDP. Think about in a scenario, if you have like 50,000 routes in your IGP domain, and you're you're allocating the labels for those, obviously the routing, your label, the LFIP database on each of the nodes will also become higher and higher based on how many routes that each node is carrying. Apart from that, the hierarchical way is proven method of reducing the load at each level. Like in a tree, you have the top node and the subnodes and the subnodes after that, and you're actually breaking down the amount of work or the processing to be performed at each node at each level, thus improvising the services. So certain services you don't even have to touch the core layer. you can only do things at the access layer or the aggregation layer and get done with it. You don't have to make changes across your whole network, whole service provider network. Apart from that, you need virtualized support. Means you can have your physical topologies virtualized as well. Like like even take an example of a VRF. If you are creating layer 3 VPN services, you can virtualize the customer domain into a separate routing table using VRF, right? Apart from these key points of scalability or convergence, you also need to focus on another aspect, which is your OAM capability. You need to have OAM capability from end to end. Even if you break down your IGP domains or your network infrastructure into different segments, you should be able, your applications that you're providing or the services that you're providing to your end customers should be able to use the OAM from one end to the another end from where they're trying to use that. And finally, it also allows you the flexibility to increase, or well, not increase, actually upgrade your network or move away from the traditional MPLS LDP into the segment routing domain. So you can actually make your whole service provider network programmable, integrated with programmable fabrics. Like, hey, I have a SDN controller sitting on top of it. I can get a full view of my topology using BGP-LS, BGP link state protocol. And then I can actually use SRT policies or regular PCE-based policies to push down the labels into the infrastructure and give forwarding path from one endpoint to the another endpoint. And you can easily migrate sections or segments of your network to segment routing without even affecting the other segments. Like you upgrade your core, and you don't even have to touch your aggregation layer or your access layer, and you can seamlessly migrate from LDP to segment routing, and you won't even face any kind of traffic loss. It'll be kind of seamless. Okay, so it gives you a flexibility to upgrade your network infrastructure to new technologies, and at the same time, you can use any kind of the access technologies that are available for your eNode Bs or your endpoints. It can be microwave, it can be TDM based, it can be Ethernet based. You can use any of these technologies irrespective of what technology you used at the access end. You can use, you don't have to make too many changes on your internal infrastructure within your core or your aggregation layer. Now, this is how your environment looks like. You have your core, you have your aggregation layer and your access layer. You build segments, you break down the segments into multiple MPLS domains. So MPLS in the core, MPLS on the aggregation and in the access layer, or MPLS just in the aggregation layer. But what happens is with this breaking of these segments, you will have to do redistribution at different endpoints, right? Either into different areas or either into different processes, you will have to do that. With seamless MPLS or unified MPLS, you don't really have to. It gives you the flexibility that you have a single fabric or single solution across your whole network, even if your network is segregated by different processes, routing processes, or different areas. Okay, so what do we have? So remember, in this topology, if you have just plain MPLS and plain MPLS running and you're doing redistribution and kind of those stuff, you will have to make changes at different attach points. We call them attach points as the points where you actually have to make some changes to your infrastructure, right? So you might have to make some changes to your core domain. You might have to make some changes on the aggregation or on the access layer. You need to minimize those operation points or those attach points where you actually need to make some changes. And with unified MPLS, you don't really have to. You only need to plug and play your new services on the access layer, and the core and the aggregation are pretty much untouched. All right, so what is unified MPLS? So unified MPLS is nothing but your classical MPLS, within which we are breaking down the IGP domains, okay, for segmentation. So now you don't really have to worry about troubleshooting one particular or troubleshooting your whole network, which is what you used to do in your whole MPLS troubleshooting process. But with now, you can only troubleshoot only part of the section, and you get to know where the forwarding is next supposed to be, and you can go to the remote endpoint of that. You have RFC 3107, which is nothing but BGP 3107. We'll talk about that in a minute. BGP 3107 allows you to not just exchange BGP prefixes, but also labels along with it. Now, quick question. How many of you know, or do you know, if LDP allocates labels for BGP learned prefixes? Yes, no? Come on, guys. I think we had some coffee before. So LDP does not allocate labels for BGP learned prefixes. It only allocates labels for your IGP prefixes. Okay, so RFC 3107 is allowing you to allocate labels and exchange those labels via a BGP update. Then you have BGP filtering. Obviously, since you have broken down the operational points or broken down your network into different segments, you have BGP being established from your access, well, depending on your design, either from access to your aggregation or pre-aggregation node to your edge to your core route reflectors. Based on your topology, you have different peerings being established at different points. You can filter out the prefixes that you want at different ends. If certain prefixes from other access points, you do not want those installed in a particular access domain, just filter those out. You don't have to do that. This was not really possible with the traditional MPLS way, because then you only need to have, you had VPN v4 route reflectors, and at the PE routers, you establish the VPN v4 peerings. You can, based on your RT import and export, you can only do the filtering there. Here, no. You can still do the filtering at different points, even on the aggregation layer, and filter out the prefixes that you want on your access domain. Okay? So these are some of the components. Then for convergence purposes, or faster convergence, you have LFA and remote LFA. So local IPFRR. So you don't really need MPLS traffic engineering tunnels. You can have local fast read out, or you can have remote LFA, loop-free alternate, which gives you or pre-calculates an alternate path and puts that in your RIB as well as your FIB as a backup. So just in case if there's any failure, you have the backup path available to do the forwarding. Right? We'll talk about those as well. Then you have BGP Pick. BGP Pick is BGP prefix independent convergence, which allows you to have, okay, so by default, BGP, even if you use route reflectors, even if you have multiple paths, it will only select one path as the best path, correct? Yes, no? Come on, guys, let's be active. Remember, Tom shared his slide, and he talked about the dungeon. This is no dungeon. So let's be more open and more communicating, right? So BGP Pick will give you an alternate or pre-calculated BGP path or backup path in case of any failure on the edge device. And then you have end-to-end OAM. E2E is not a terminology. It's just that there was no space, so I wrote E2E. It's end-to-end OAM. So you have the capability of using OAM services across from access layer to the remote access layer, crossing across your aggregation and your edge or your core layer. Okay? Now, this is what combines to form your whole unified MPLS. On top of that, you get the flexibility of using any kind of access infrastructure. So you can have your microwave technologies, you can have your Ethernet, like I said before, TDM, any of that, you can use that along with your unified MPLS. And what does unified MPLS provide us? It provides us with scalability, because you can deploy any kind of services without making any changes to other parts of the network. security as well, because you're doing filtering, so you limit the amount of prefixes or the specific prefixes that you want in a particular segment or not. Simplification, obviously you don't complicate your whole network. You have nodes on your access layer which are less powerful, and you do not want too much processing to be done there. So you simplify the processing on those nodes, which is not required on, they're not even capable of handling. Multi-services, like we explained before, you can deploy different kinds of services at one go. And I have not mentioned here, but it also gives you the flexibility to make or upgrade it to a programmable network. Okay. So what is RFC 3107? Allows you to, like I said before, allows you to exchange the BGP prefixes and the label information along with the prefix. So what you can do is, just for the sake of if you haven't tried or experienced how BGP 3107 works, you can take two routers, maybe in a GNS3 or any virtual environment, and establish address family IPv4 link state peering between those two routers, and advertise a BGP prefix from each end, maybe just a loopback, and see what kind of update you're getting. You will see that IPv4 prefix along with your label allocated to that prefix. You will see both that information. And when you do, you look at the BGP prefix in detail, you will see that label value associated over there. So this is helpful, and you don't really have to rely on LDP for the BGP 3107 to work. So at points, you don't even need LDP if your devices doesn't support. LFA, so look, IPFRR, it's what it's called, defined in RFC 5286. It's a local protection mechanism wherein if you have like 3 node topology, A, B, and C, and there's a source behind A and the destination behind B, if the path is from A to B and the link between A and B fails, the routing protocol has pre-calculated the path that if this link fails, you need to go from A to C to B, right? This is pre-calculated rather than on-the-fly calculation that when the link failed, IGP reconverged and calculating the new path, giving you, and then installing in the fib. No, you don't really need to do that. IGP did that job beforehand and calculated and updated the RIB and the fib with the backup path. Now, the problem with this is it does not help with certain topologies. Now, in this 3-node topology, it works fine. If there's a ring topology with multiple nodes, this fails. So what happens? Before going to the remote LFA, I'll come back to remote LFA. Let's look at this topology. If you have C1, which is carrying traffic towards A1, A1 is the destination. Now, if C2 wants to send the traffic to A1, it is going from C2 to C1, A1. If the link fails between C2 and C1, C2 will route the traffic to C3, and C3 might route the traffic back to C2 because of your LFA stuff, right? So it might break. Now, in that situation, you have is remote LFA, wherein it uses the PQ algorithm. It's defined in the IETF draft. The PQ algorithm calculates a node in the topology, which is the kind of a mid node or a point from where you can, first, if the link fails, you move the traffic to that particular node, and from that node, you will find the path to your destination. Okay, so those PQ nodes are actually the ISIS or the OSPF process pre-calculates it when they're performing the SPF calculation. It finds the backup path. It forms a backup tunnel to that PQ node, which is the node in the middle. And when the link fails, the tunnel becomes activated, and the traffic is routed to that. So you don't really have to worry about, hey, my link failed, and we are running into some kind of traffic black hole. You don't have to worry about that. Now, with remote LFA, you can have the faster convergence. Let's see how this remote LFA works. So in the same topology, you have, if you look at the C2, the lib of the C2, you have label number 20, which is for A1, label number 99, which is for C5, which is the prefix, the label allocated by C3, and you have the FEC of A1 on C5, which is label 21. So if the link fails, what it's going to do is, hey, I have this link failure. I push on this label number 99 and say, go to C5, and then 21. Say, OK, from 99, I go to 21, and this is how I converge. I don't have to do too many lookups or too many calculations to find a backup path. They have pre-calculated, and you can actually look at, when you look at your IGP table, you will always find the PQ node, which is the PQ node in the topology, and it'll show you the backup tunnel interface. Hey, this is the tunnel to that particular PQ node, and route the traffic back to your actual destination. BGP Pick or BGP FRR. Now, what happens is with BGP, you have suppose 2 PE routers providing multi-homing, or even if it's not providing multi-homing, it's having the route to the destination that you want to go via multiple paths or single path. Now, what happens is BGP will calculate one best path. If that fails, it will route to the other topology, okay? Other P router, and that calculation will take some time. The convergence time will increase. In that scenario, what you do is, rather than doing that, in BGP Pick, they point the next hop to an index value. So a pointer in the memory. And that pointer, if the primary link fails, the pointer is changed to the backup. Like you do in IGP, similarly in BGP, it's just that now rather than pointing to the next hop, they're pointing to a particular pointer, and that pointer is changing to the backup device and routing the path. And that backup is also getting installed into your RIB and the FIB accordingly. All right, so we have few models here that are supported with unified MPLS. I'll not go over here. We'll probably go over the designs directly. You have small networks based on like up to 1,000 nodes, and then you have large-scale networks where you have you scale up to 100,000 nodes. Okay. So I'll just go over these quickly. In this, the small topology where you have less than 1,000 nodes, you have a single IGP domain, and you do not have, and you have your access network where you are running your microwave or your fiber network or 3G LTE services. In this topology, you use a single IGP and your LDP domain. You don't really need BGP 3107. Now, if you scale this further and you are running IGP onto your IGP and MPLS onto your access layer as well, in that scenario, what you can do is you can have BGP 3107 being established end-to-end from your access to your pre-aggregation to the remote pre-aggregation via route reflector, of course, and from there to your remote access layer, right? So you exchange your prefixes with labels, and within your IGP domain, you do the switching using your IGP labels, which is allocated by via LDP, okay? In the large-scale design, now in this design, what you have is you have point-to-point connections. If you look at the last endpoint, you have point-to-point connections. You do not have the scalability or support for MPLS or IGP towards your E-node Bs. You have your aggregation layer running your IP and MPLS core aggregation. Similarly here, in this, what you do is you run IGP and your LDP from within your each domain, and across from pre-aggregation to your aggregation end-to-end, you run BGP 3107 to exchange the labels for your end host or your access layer. Now, this gives you, so when you're actually forwarding the traffic, you will have your top 3107 label. And well, when it reaches the particular aggregation layer, but from your aggregation to the remote aggregation, you will have your IGP label, which will be added on top of the stack to do the forwarding, popped further to your network, okay? Now you have another large-scale design. In this, your IGP domains, or your access layer supports IP and MPLS. Now in this, what you can do is, like you did in small-scale networks, you can use, or you can run BGP 3107 across your whole network end-to-end and exchange the labels along with the prefixes of the access layer. You don't really need, now remember, your pre-aggregation layer usually will be having your different routing process for your access layer, and it might not even, those routing processes will not even be redistributing the prefixes. It's only via BGP 3107 that you're exchanging the labels and the prefixes, and you know how to reach the core. And from core to the remote devices, again, your IGP-based forwarding within your IGP domain, and then BGP 3107 coming into play. This is another topology that is supported. In this, what happens is your end-to-end infrastructure does not support 3107, but it is only supported till your aggregation or pre-aggregation layer, right? So your access layer is not supporting 3107. It's supporting IP and MPLS infrastructure, your features, but not the 3107 stuff. So from here, you will have your LDP-LSP till your aggregation layer. From aggregation to the rest of the network till the remote pre-aggregation or aggregation layer, you will have your 3107 along with your IGP domains. And the remote, again, moves on to your LDP-LSP. Now here, the redistribution may happen between the processes because you do not have the information across the access layer. All right, this is a sample topology of how the forwarding will look like. So we have broken down into access network, aggregation core, aggregation access. And if you see here, you have your, on the first level, you will have your IGP label on top of, which is having a BGP label on the bottom, and then your IP prefix or your service label, based on if you're the VPN v4, and your pseudo wire label, your L2 VPN label. As the packet moves further and reaches one of the edge nodes or ABRs, the label is popped. You only have your BGP 3107 label, and based on the prefix exchange via the BGP 3107, you get a new label. You swap that label, again within your IGP, push pop, end-to-end, right? So what we are actually getting here is simplified end-to-end transport. You have the OEM capability. You have flexibility of using any kind of, or providing service to any kind of infrastructure, be it LTE, 3G. And you're also making it scalable using your hierarchical BGP, which is 3107. So the main game is actually played by the BGP 3107 in this unified MPLS, along with other technologies. All right, that's it from my side.